Thanks for watching. If you find my videos helpful, please like, share, and subscribe. And please look in the description beneath this video for useful links to other videos and resources to help you learn chemistry. For today's video, I'm going to teach you how to answer the question shown here. I invite you to pause the video right now and try this question on your own first, then hit play and I'll show you how to do it. So I readily acknowledge that this is a question where you read it and it seems dizzyingly complicated. To help us though, I just started by writing down all of the information provided. It gives us an activation energy. It tells us that we have a rate constant, and I'm just going to use the term K1 here to represent that initial rate constant. And then it tells us that we have a new rate constant after we change temperature that is 4 times the original rate constant. So the new rate constant that I'll call K2, written here that it's equal to 4 times K1. It tells us the initial temperature is 298 K, and then it asks us what is the new temperature that is going to make this new rate constant be equal to 4 times the original rate constant. In other words, what is T2? Now, as you look at all this and think, how in the world could I solve this? It might help, depending on where you are, what your class is, what your instructor's shown you, or if you're in my class, to look over your cover sheet on your exam, or through your notes or lecture slides on a problem set to find an equation that includes all of these components: a rate constant, another rate constant, 2 temperatures, and an activation energy. And what is that equation? It's this one right here called the Arrhenius equation that I've talked about in another video linked to in the description below. Now, as it turns out, because rate constant 1 and 2 are proportional to each other, that is K2 is just 4 times K1. It doesn't matter what number you start with for K1. I could just make it easy and set K1 equal to 1. And because K2 is 4 times that number, it's going to be equal to 4. All I do then to solve for the missing temperature, that is T2, is I insert all of these numbers down here into this equation and then use the magic of algebra. So let's go ahead and do that now. Now, what value of R do I put here? Well, as it turns out, in this case, because we're dealing with energy, specifically activation energy in units of kilojoules, the version of R that I'm going to use, the ideal gas constant, is going to be this one right here, 8.314 joules per mole Kelvin. And the giveaway, of course, is the fact that I have joules here and kilojoules up there. I need energies to relate to one another. Now, of course, the one issue here is that these units don't match. Kilojoules and joules, I'm going to have to make those match by converting them both to the same units. I think for me, the easiest way to do that is to convert these kJs per mole into joules per mole, as shown right here. I end up getting 50,000 joules per mole as my activation energy. So I'll make that substitution right now. From here, it's just number crunching algebra. 4 divided by 1 is, of course, 4. Natural log of 4 is 1.386. Now, as I divide 50,000 by 8.314, you'll notice unit-wise that my joules cancel each other out, my moles cancel each other out, and I have kelvins in the denominator of the denominator, which means they're really in the numerator. So this term right here all simplifies down to 6,014 kelvins. The beauty of the kelvins is it's going to cancel out the kelvins down here when I multiply through. So let's go ahead and do that. Multiplying this term here by each of these, and then simplifying here on the right, I end up getting this equation right here. I will now subtract this term from both sides to get this number right here after rounding to the correct number of significant figures. Now I need to isolate T2, so I'm going to multiply both sides by T2. So T2 is neutralized on the right, and the equation then simplifies down to this right here. To now finally isolate T2, I need to divide both sides by this number, negative 18.80. And when I do so, I'm of course left with the units of kelvins, which I should get for my T2. I nullify that side and get T2 being equal to 320 kelvins, which is answer B.